Hello and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last couple of lectures, we have started out our foray into ML model training, and we started with the gradient descent algorithm, and we went quite deep into understanding why the algorithm works, right? In today's lecture, we will go into the more practical aspects of model training, which will allow us to determine the value or the amount of the learning rate that you should use, and then we will talk about some modifications to the gradient descent algorithm that are really required for very large amounts of data, right? Especially if you're training huge models like neural networks with tons and tons of data, billions of parameters and data points, then clearly you need training algorithms that are very efficient. So that will lead us to the concept of stochastic gradient descent, and we will later on also explore various types and modifications of the stochastic gradient descent or SGD algorithm. So let's go ahead and get started with this lecture. So the topic for today is the practical aspects of ML model training with gradient descent. Okay, and the first thing that I want to address here is the concept of the learning rate. So for your recollection, if you have the gradient descent GD update equation, parameter update equation, right, that is basically your beta vector at k plus 1th iteration is the beta vector at the kth iteration minus gamma times the gradient of the loss function at beta k, right. So this is the update equation. L, as you know, is the loss function. The nabla sign indicates the gradient operator, and this gamma is the learning rate. Beta is the vector of parameters and k is the iteration number. So an important question arises, how do we pick the value of the learning rate? How do we choose the learning rate gamma? Okay. So the learning rate decides how aggressive the optimizer is, and can be tuned by examining how the loss function value changes as the training proceeds. So basically we have to monitor the loss function and see how it is changing. So it can, hopefully it is reducing, right, but in some cases if your optimizer is too aggressive, you can in fact increase the value of the loss function even, right. So what you do is you plot the value of the loss function L as a function of the number of iterations. And we were using the index k for the iterations. So there can be a few scenarios that can pan out. Your loss function versus iteration number curve, let us say you start at this value of the loss function and that corresponds to whatever initial guess you have taken. So this point depends on the initial guess assumed for the parameters, right, will decide that value, right. So the value would be basically the loss function as a function of the parameters at the 0th iteration. Let us say there are p parameters, so b1 0, b2 0 up to bp 0. If you plug these into the loss function, that is the value you are going to plot at iteration number 0, and then as the iterations proceed, as the model trains, you expect that the loss function will come down. The model is learning, right, it is getting trained. So this is sort of the ideal scenario that you would expect, right. So one may call this let us say a good learning rate or an optimal learning rate, right. However, there are other possibilities that can happen, right. For example, if your learning rate is too low, then your model may take too many iterations to converge to the right point, right. So for example, this could be a very slow learning rate, and to get to the desired value of the loss function or the error, right, it may take a huge number of iterations, or maybe the model may even saturate and the loss function may not go down. So this is a low learning rate or a too small learning rate, right. So your learning rate can be good or optimal, it can be very low, or it can even be very high, right. So for example, your model was so aggressive that instead of going in the direction where the function is decreasing, it went off in the completely opposite direction, and I will show another pictorial representation where this becomes clear why that is happening. So your loss function could actually explode, right. So here the learning rate is too high. So this is the case of a too high learning rate, right, and essentially the loss function is increasing. So the loss function increases with iterations due to some instability, right. When the learning rate is too small, then you need too many iterations, and when you are having a good learning rate, then the model converges in a reasonable number of iterations. So here we plotted the loss function as a function of the iteration number. One another way to visualize what is really happening is to plot the loss function as a function of the parameter, right. So in principle there are p parameters, right. So it is going to be very difficult to graph a multi-dimensional space where we are trying to look at how the loss function changes as a function of all the p parameters, but we can certainly pick one of the parameters and then see how the loss function curves look. So that is what we are going to do next. So we are going to examine now the plots of the loss function versus let us say one of the parameters, or maybe this is a very simple ML model with just one parameter. So how would that kind of a plot look for all these three cases, right. So you have too high a learning rate, you have too low a learning rate, and then you have an optimal learning rate. So how would these cases look, right. So let us first start with the very high learning rate. So if your learning rate was too high, right. So if your learning process was too fast, then if you plotted the loss as a function of beta, that is the only parameter we are considering, and let us say for the purpose of the discussion the loss function is quadratic in nature, looks something like this, right, and therefore the optimal value of the parameter is here, right. This is the parameter you want to converge to, right, and you may be starting somewhere here, right. So the idea is as the optimizer proceeds you want to fall into this well and then reach the local minimum. However, if you are too aggressive, if the learning rate is too high, instead of landing somewhere here you may overshoot, right. If you had to land here, you had to traverse this distance in terms of beta. This is where you would have come, but let us say your gamma was so high that you overshot and reached somewhere here, right. So what would happen then, right, instead of the loss function reducing, it sort of remained the same or perhaps could have even increased, right. So that is where you came, and then the next time you tried to fix it, but again it was too high, right, the learning rate. So maybe you reach this point and then you reach some point here and then this sort of continues, right. So I hope you can see how if the learning rate is too high, the model may not converge. To the optimal parameters. Right. So this is a case of too fast learning, right. So we want to avoid this. The next case can be when the learning rate is too slow. And in this case, let us say again we plot L beta as a function of beta, we are going to assume the same shape of a loss function as a function of the parameter that is chosen, and again we are starting somewhere here, right. So in this case the model is too slow, so it takes very small steps along this curve. You reach here, then you reach here, then you reach here, right, and so on, right. You keep on falling down the well, which is nice, but perhaps it took way too many iterations to reach here. So by the time you reach here you have wasted a lot of computing power. As you know, ML models can take a lot of computing power and these are often trained on GPUs. So we want to be careful in terms of the amount of compute we are consuming, right. So if the learning rate is too low, the model may take too long to train, or sometimes it may not even finish the training, right. So it is basically wasted computational power on the scores of CPUs and GPUs that we are using for machine learning applications. And lastly, if you have an optimal rate, that is where you want to be, right. So this is the perfect or optimal and as I said, you can only determine this by looking at how the loss function changes as a function of the number of iterations. It is not practical to make L versus beta plots. I already said that your model may have millions or billions of parameters. You can't really make a plot of L versus any of your parameters, right. Instead you see L versus iteration number, but here we are plotting L versus beta just to get some physical insight into what is really happening. So again the curve looks something like this, and then you start again here, but this time your learning rate is optimal, so that you are taking bold and broad steps, and finally within fewer iterations than in the previous case you have reached the local minimum, right. So here the model converges rapidly to the optimal set of parameters. Right, and in these cases mostly you should note that I have plotted what is here the training loss. Typically one also plots a validation loss separately to make sure that the model is not overtraining or overfitting or underfitting, right. So to avoid over or underfitting, one must look at both the training error or the training loss and the test loss, the test set loss, or you could call it validation loss, to ensure the model is optimally trained. Okay, I hope this makes sense to you as to why to avoid under or overfitting. One must look at both the training loss and the test or validation loss. In case the training loss has really come down very fast, but the validation loss is not coming down as fast, then clearly it is a case of overfitting and you may have to change your learning rate or make some other tweaks to the model training procedure. Okay. So to summarize this part of the discussion, whatever we discussed right now, there are three cases, right, in terms of the values of lambda that you can assign, values of gamma that you can assign during the training process. If you have very high learning rate gamma, then there is an instability in the algorithm and your loss function may just explode, right. It will keep on increasing and increasing and you will never converge. You could have a very small or very low value of the learning rate which would lead to very slow convergence and wastage of computational power. Right, and you may never even converge to the right set of parameters. The last case is that of the optimal learning rate, and this leads to fast and reliable convergence of the gradient descent algorithm. To find the optimal set of parameters. Okay. So now we will go forward in our discussion, and like I said, the gradient descent that we have discussed so far, that is the plain type of gradient descent, and in practice there are some modifications you make to the gradient descent algorithm to make sure that it is amenable for large kind of data sets. Okay. So we will look at two types of gradient descent in our discussion. So these are the types of gradient descent. So there is something known as batch gradient descent, and there is something known as stochastic gradient descent. SGD. Okay. So what's the difference between these two? The difference is that in this case the gradient of the loss function is computed on the entire data set. Okay. What do we mean by this, right? So let's take the example of the mean squared error loss function. So the L2 loss or the mean squared error loss looks something like this. It's basically 1 over n sum I going from 1 to n yi true value minus the predicted value yi hat whole square. So in principle you have to sum over all the data points, right, and you have to compute the deviation for all the points, and this is what is meant by the entire data set. This summation is going from 1 to n, where n is the number of data points. If that number is in the millions or billions, then you will spend forever just computing this sum and the value of the loss function and the gradient of the loss function, because you have to take the gradient of this loss function with respect to each of the parameters, right. So yi hat, if you remember, depends on the model parameters, so there will be a chain rule that has to be applied and so on and so forth. But the crux of the matter is, because this summation runs over all the data points, we spend a lot of time just computing this gradient. So that's the problem in this case. On the other hand, in stochastic gradient descent, what we do is that the gradient is computed with just, in the extreme case, one data point or a collection, right, a small collection called the mini batch, which is used to train the model. Okay. So this is the major difference, right. The gradient is computed with just one data point. So basically you pick the data point for which you are computing the loss function, and then the gradients also are computed with respect to that point, or a small collection of data points. If you do not want to use all the n points, maybe you use n by k points, right, where k is a large number, and that way you do not spend too much time sort of just computing the gradients, and your algorithm can proceed slightly faster. Okay. So these are the two alternatives, batch gradient descent and stochastic gradient descent. So let us see what the difference is between these two. So the batch gradient descent is obviously more accurate. Why? Because obviously we are including the entire data set, so that means that we will have full information on how the loss function changes when the parameters change. Each and every data point in the training set is accounted for, right. So it is more accurate, but the problem is that it is very expensive on large data sets, leading to slower but stable convergence. So generally the convergence will be more stable because all the points are accounted for, so you will not be influenced by one outlier. So suddenly it will not happen that the loss function has shot up and you are trying to act against it by changing the parameters, right. So it will be more reliable convergence. Now in the case of the stochastic gradient descent, it can lead to noisy parameter updates. Like I said, your loss function depends in one iteration on only some of the data points, or in the extreme case on only one data point. So large deviation in that data point, this yi minus yi hat, could lead the optimizer to behave more aggressively, right. So this can lead to noisy parameter updates, but it is inexpensive and thus can lead to faster convergence. So a whole series of algorithms have been developed to take care of this point, right. The parameter updates are quite noisy, right. So this is clearly a drawback. The other things are advantages. It's an advantage that it is inexpensive, it's an advantage that it leads to faster convergence and so on, but the one drawback, the major drawback, is that it leads to noisy parameter updates, and therefore a lot of research has gone into designing variants of the stochastic gradient descent algorithm, and these variants have proved to be quite useful. Okay, so what I will do next is I will introduce a few more parameters that are used, right, when we discuss about training of machine learning models, and then we will end today's lecture, and in the next lecture we will cover the variants of stochastic gradient descent. So in the context of model training, if the data set has n samples or n data points and we use the mini batch approach, mini batch stochastic gradient descent, with a batch size small b, then there is a term that is defined, it is called an epoch. So then an epoch or one epoch, so one epoch is the elapse of n divided by b gradient updates. So if there are n divided by b gradient updates and every batch has a size b, then that means we have looked at n divided by b times b number of samples, right, whereby the model has seen all n divided by b times b. So that is n samples once. So one epoch is the elapse of n by b gradient update, so that the model has seen all the samples, right. So in other words, an epoch is one complete pass through the entire training data set. Of the ML model. Right, and typically one uses multiple epochs while you check both the validation and train losses. So you continue the training for several hundreds of epochs if possible, but definitely examine both the training and the validation losses. So the training and validation losses are examined as a function of the number of epochs right, because that is when the parameters are updated rather than as a function of the number of iterations which I had mentioned earlier, and this is particularly true for complex models like neural networks. Alright, so with this I come to the end of this particular lecture. In this lecture we discussed the concept of the learning rate and how different values of the learning rate can lead your model to converge reliably, or it can create problems where the loss function simply explodes due to an instability in the gradient descent algorithm. And we saw plots of the loss function as a function of the number of iterations, the loss function as a function of one single parameter, and we got physical insight into why the gradient descent algorithm can not converge in some cases. Finally, we discussed the concept of stochastic gradient descent, wherein with large amounts of data set you work with subsets or mini batches of data set to save on your computational power of model training, and this leads to the concept of an epoch, which is the number of iterations over which the model has seen the entire data set right once. And the other important thing is that you have to examine both the training as well as the validation losses as a function of the iteration number for simpler models or as a function of the epoch number for more complex models, and if you do that you can prevent under or overfitting of the model. So I hope you found this lecture useful. I look forward to seeing you next time, and thank you for joining.